Okay, so waves, question 1. So figure 1 shows a slinky spring used to model a sound wave. Okay, so when the sound wave gets, this is the spring you probably would have seen the demo in class. Teachers are pushing it forwards and pulling it backwards. Label the arrows on figure 1 and choose the answers from the box here. Okay, so we're looking for, there are 3 things in total, it's 3 marks. So there's 1, 2, 3 different labels to use. So we're going to look through amplitude, that's the height of the wave from the rest point. Compression means squashed. Okay, well that one goes there, so that's going to be a squashed bit, a compression. That's that done. Frequency, number of waves in 1 second. In 1 second. Okay, well I'm not going to, I've got no idea what the time is here, so it's definitely not, that's not going to be in there anywhere. Refraction and wavelength. So I've got these 3 now left with 2 boxes. The wavelength is the distance between identical points on a wave. Identical points on a wave. Okay, and that in this case is here. So we've got compression here. That's going to be our wavelength there. So that's out. So it's between these 2, refraction and amplitude. This is a difficult word, this one. It's the opposite of squashed. So refraction means stretched. Okay, so it's going to be a rarefaction. Okay, now the amplitude, just a sort of way of trying to remember this, the amplitude is the distance. We only really ever talk about amplitude, it happens with both waves, but always. But we generally talk about amplitude being the distance displaced from the rest point there. Okay, it's the height of the wave or the depth of the wave. Right, next question. What type of wave is a sound wave? Electromagnetic. So we know the electromagnetic waves, rich men in Vegas use X-ray glasses. All these waves travel at the speed of light. All of them can travel through a vacuum, and sound is not one of them. So radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. So it's definitely not that one. So longitudinal, transverse. Transverse, we have oscillations at right angles. So transverse, so we use T, transverse. Transverse is oscillations at right angles to the direction of travel. Longitudinal oscillations are in the same direction as the direction of travel. So there's only ever 2 lots of movement, forwards and backwards, or up and down, in the same in one direction, whereas here there are 2 planes of movement with a right angle between them. So if we're looking here, this is modelling sound waves. This is moving forwards and backwards, the hand squashing forward, and the wave is moving that direction as well. So the oscillations are in the same direction as the direction of the wave, which means sound is most definitely a longitudinal wave. Really important one that you remember that. So next question. Let's see. Lost on the screen. So figure 2 shows 2 students measuring the speed of sound in air. Here we've got a stopwatch, we've got bricks and a wall. One student bangs 2 bricks together. The sound wave produced is reflected from the wall and travels back to the students. Describe how they can determine the speed of sound. So what's going on here? So let's just check. So we've got this student is hitting the bricks together. The sound then travels to here. The sound wave is produced, is reflected from the wall and travels back to the students. So the student bangs the bricks together. The sound wave then travels back from there like that. Okay, so we've got travels that way to begin with, and then travels back this way here. Okay, to which that student there, so as soon as the student hears it, as soon as that student hears it, they're going to stop the stopwatch. So that's what we're working out how to do that. It's worth 4 marks. So it's 1, 2, 3, 4 things to say. Okay, so the first thing is we're going to describe how to calculate speed. Doesn't matter the speed of sound, it's speed. So we know that speed equals distance travelled divided by time taken. So in this calculation here, we're going to have to work out how to find these two things. We're going to describe how to find the distance travelled. Well, the distance travelled by the sound is from there to there. So distance is to the wall and back. So we've got to measure distance from students to the wall. Okay, what we're going to use, we might need a tape measure. So always try and say what we're going to use using a tape measure. You might decide to use meter rule, okay, that's fine, but say what you're going to use. So measure the distance from students. So distance, the sound travels twice the distance to the wall as it goes there and back. Okay, so we're just saying we know that the sound then travels twice that distance. How do we record the time? The student with the stopwatch starts when he sees the bricks hit together and stops when he hears sound echoed. Okay, so we know that echoed is just a reflected sound wave. This is the time taken. So there's quite a lot we could write here. It's only worth 4 marks, this one. So we don't need to worry too much about doing this. We've already said speed, distance, time. Other bits we could write here. We could always write repeat. Okay, so repeat to get more results. More results. Okay, we could then, we could always remove anomalies. We could always take an average. Okay, so things that we could always do at the end of any experiment. We could always repeat the test again to get more results and test reliability. Okay, that's why we do it. We're testing reliability to improve reliability. We trust it more if it comes up the same as every result is the same. We trust that result much more. We always remove anomalies, and if we can, we always take an average as well. Okay, but those last 3 are just sort of extra ones that you could write if this was a 5 or a 6 marker, or you have no idea what else to write. Okay, take care. Hope that helps.